Okay, this section is about the dot product of two vectors. And it is one of the most kind of important concepts in math, algebra. It appears everywhere. So suppose, let's start with two-dimensional case. Suppose we have two vectors. We have a vector u, it has some coordinates. Let's show the coordinates of u with u1 and u2. They're just two numbers, say 1 and 2, for example. And suppose we have another vector, v1 and v2. So if you look at the plane, we have two vectors, u and v. The inner product or dot product are two names for it. There are two names for the same thing, inner product or dot product of these two vectors u and v, which we showed with u dot v is equal to u1 v1 plus u2 v2. Very simple. So for example, let's look at an example. Let's say we have a vector u equal to 2 and 3, and we have another vector equal to 4 and 5. The vector u, the coordinates of u are 2 and 3. So this is u. And the coordinates of the vector v are 4 and 5. So this is the vector v. What is the inner product of u and v or dot product of u and v? It's just multiplication of the first coordinates, 2 times 4, plus multiplication of the second coordinates, 3 and 5. 2 times 4 is 8, 3 times 5 is 15. Their sum is 23. So dot product, in dot product, we have two vectors. So we have two vectors. We multiply them, we get a number, not a vector. So the result of inner product of two vectors is a number. We have two vectors, we multiply them, we would end up with a number. Here we get 23. Okay. We can define the same thing for three-dimensional vectors. So if we have three-dimensional space, which we showed with R3, if we have two vectors here, u and v, the coordinates are something like u1, u2, u3. These are just three numbers. And the vector v has coordinates v1, v2, v3. These are another three numbers. U and v, they would look like something like this. The inner product or dot product of u and v is equal to u1, v1 plus u2, v2 plus u3, v3. So for example, if the vector u is 1, 2, and 5, and the vector v is 3, -2, and 7, the inner product or dot product of u and v is 1 times 3 plus 2 times -2 plus 5 times 7. 3 times 1 is 3 plus 2 times -2 is -4. 5 times 7 is 35. Well, the sum is 34. So the inner product of u and v is equal to 34. We multiply, we compute the inner product of these two vectors, we again end up with a number. Okay, so we have inner product in dimension 2, we have inner product in dimension 3. We have inner product in every dimension. We can have higher dimensional vectors and we can compute the dot product. We would get the same thing. Now, let's look at a few, let's look at another way of computing inner product. So let's say we have two vectors u and v. U has coordinates u1 and u2. V has coordinates v1 and v2. U dot v, as I said, is equal to u1 v1 plus u2 v2. But there exists another way, a second way to compute inner product. So this is the first way. To compute the dot product. There is a second way to do that. What is the second way? The second way, there's another way. It says the inner product of u and v is equal to the length of u times length of v times cosine of theta, which theta is the angle between u and v. So here, if on R2, if you look at the vectors u and v, you can look at the angle between them. Let's say that angle is theta. That gives us a way to compute the inner product by multiplying these two, the length of these two vectors and the angle between them. So let's look at some examples. So suppose we have two vectors. Example. Suppose we have two vectors, u and v. And suppose we, so this is say this is u, this is v. Suppose we know u, the length of u is 1, the length of v is 2, and suppose we know the angle between them is pi over 6, right? The point is that we know the length of u, we know the length of v, we know the angle between them, but we don't know the exact coordinates of u and v in this question. And the question is, what is u dot v? What is the inner product of u and v? Now that we don't know the coordinates, we should use the second way to compute the inner product. The second way says the inner product is norm of u, the length of u, the length of v, and cosine of the angle between them. So here length of u is 1, length of v is 2. We should multiply by cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. So we would get 1 times 2 times radical 3 over 2. We get square root of 3. That would be inner product of u and v. Okay. Now, the interesting thing is that sometimes we can use this idea to compute the angle between u and v. What does that mean? So let's say we have a vector u. Let's say u is 1, the vector u is 1 and 2. And we have another vector v with the coordinates 2 and 3. And I'm asking you, find the angle theta between u and v. So this is u. Did I choose good numbers? This is U, and then we have V. This is U, and then the coordinates of V are 2 and 3. This is V. I want to compute the angle theta here between U and V, okay? The idea is that I know there are two ways to compute the inner product. There are two ways to compute the inner product. One way is just by multiplication of the coordinates of U and V. We should multiply first component of U by the first component of V plus. We should multiply the second component of U by the second component of V. So 1 times 2 is 2, 2 times 3 is 6. The sum is 8. So the inner product of U and V is 8. We use the first way of computing inner product to compute that. Now there was a second way. The second way tells us the inner product is equal to the length of U times length of V times cosine of the angle between them. Okay. What is length of U? How can I compute the length of U? Well, the length of U, remember, is equal to square root of sum of squared of its components. The norm of the length of U is equal to the square root of 1 squared plus 2 squared. That's the way to compute the length of a vector. It would be square root of 5. How can I compute the length of V? It is square root of 2 squared plus 3 squared. It's square root of 13, right? And theta is unknown. I don't know what is theta. I don't know what is theta, therefore I don't know what is cosine of theta. So the second way tells me U dot V is equal to the length of U, which is the square root of 5, times the length of V, which is square root of 13, times cosine of theta, which I don't know what is that. But note that at the same time, the first way actually tells us U dot V, this inner product. We know what is the value of inner product. From here, it says the value of the inner product is equal to 8. So square root of 5 times the square root of 13 times cosine of theta must be equal to 8. There is no other way. These two different things, they're supposed to give us the same answer. There are two different ways to compute the same thing. Now, if I divide both sides of this equation by square root of 5 and square root of 13, maybe I should go to the second page. So square root of 5 times square root of 13 times cosine of theta equals 8. I can divide both sides by square root of 5 and square root of 13. On the left side, I would get cosine of theta is equal to 8 over square root of 5 times the square root of 13. Okay, what is this number? We can use calculator to see what this number is. 8 over square root of 65. This number is equal to 0.992277, etc. Okay, here you can use calculator. Not in the exam though. In the exam, it wouldn't be hard to compute. I would give you something in the exam which is, you can compute it without calculator. So cosine of theta is, I would talk about that. Yeah, that's a good question, Rebecca. Yeah, there are ways to imagine, to see what is the intuition of the inner product. So cosine of theta is equal to 0.992277, etc. What is the angle theta which its cosine is equal to that? Can anyone tell me how we can compute theta? Well, we can use calculator. Yeah, it's inverse trigonometric function. It's called arc cosine of that number. Well, we are allowed to use calculator here. It's okay. No, I think it's not going to be no. Let's say no. In the exam, I would definitely give you questions that you don't need calculator. I would just give you questions which, you know, they would have numbers like 1, 2, 3, -2 in them. I wouldn't give you a question which has like these scary numbers. Okay, and let's compute the cosine inverse of this number. Okay, the answer is theta is almost equal to 7 degrees, which is equal to 0.1 radian. It really doesn't matter. It's something around 7 degrees. So the point is that using this method, we can compute the angle between vectors. So if we go back to the previous page, if you look at this theta here, you can guess it should be a very small angle, and the angle is actually something around 7 degrees. It's a very, very small angle. Let's look at another example. This is quite important. So we can compute a few more examples. Let's say we have vector v equal to 2, -2, and we have vector v equal to, say, 3 and 5. Find the angle between u and v. You can compute that now. I would give you 1 or 2 minutes to compute this. It is important, so it's better to do it yourself. Just go and get a piece of paper and a pen and compute that. Okay, I would wait. I received 2 answers, now 3. We have 75 point something. We have 180. We have 4. We have 96 point something. We have 99. It seems we have a lot of 104.
I have a question.
Yeah, sure.
So when you're doing u times v and you're doing u1 v1 plus u2 v2.
Yeah.
I'm doing that part, and like, so I got -4 for that. But would you keep it as -4? Because if you keep it as -4, then the value of theta is I mean, it's not negative, but it's like backwards. Well, it doesn't, right? It goes like backwards of 0.
Mm-hmm. I see. Okay.
Does that make sense?
Yeah. Okay, I would explain that. That's a valid question. Let's keep that when I'm computing it. We would see what is going to happen. Okay, any other comment or any other potential answer? Arc cosine of, okay, we have another answer, which is arc cosine of minus 4 over square root of something. Square root of 272. We have more 104. Okay, let's see. Okay, so let's compute that. Let's the idea is that we should use the two different ways we have to compute the inner product, right? We should use inner product using the first way. It would be 2 times, it would be 2 times 3 plus minus 2 times 5. So we have 1.812. That's radians. Yeah. Yeah, makes sense. So yeah, probably it's close to 104. So we would get 6 minus 10, which is minus 4. Yes, the answer to the inner product is minus 4. We keep it as negative. That's the answer. We don't change that. The second way to compute it was to compute the length of U, length of V, and then they say there should be some theta between them. It should be cosine of theta. Okay. Now there's something I want to mention. Our vectors are 2 minus 2 and 3 and 5. Let's call this one U, let's call this one V. Before giving an answer, we can always look at these two vectors and guess what the answer should be, right? So we have 2 and minus 2. And that's U. We have 3 and 5. That's V. Okay. So that's theta we are looking for. Probably would be a little, it should be a little, I should just slightly better thing. It should be something like this. That would be theta. Okay, we have another answer to 265. Okay, so U dot V, using the first way, U dot V is equal to 6 minus 10, which is equal to minus 4. The second way, U dot V should be length of U, length of V, cosine of theta. What is length of U? Length of U is the square root of the sum of the squared, the components of U squared. So it would be 2 squared plus minus 2 squared. So it would be 4 plus 4, which is 8. So it would be square root of 8. What about V? The length of V is the square root of the sum of the components of V squared. So it would be 9 plus 25. It would be 34, right? So the inner product of U and V would be square root of 8 times square root of 34 times cosine of theta. Now, let's compute that. So square root of 8 times 34 is equal to 8 times 34 is 272. And its square root is 16 point, say almost 16.5. Okay, so U dot V is equal to times cosine of theta. So is equal to, well, one answer tells us it's minus 4. The other one tells us it's almost 16.5 cosine of theta. It means cosine of theta is minus 4 over 16.5. Okay, so cosine of theta is arc cosine of -4 over 16.5. Okay, therefore theta is arc cosine of this number. And using calculator, theta in radians would be 1.8. And in degrees, it would be 104 degrees. And so although cosine is negative, theta is not negative. So look at, so that's the answer. Using calculator, we would get 1.8 radians and 104 degrees. So I would just, maybe it's good to talk about that. We have the first quarter, the second quarter, third quarter, and fourth quarter. So if you have an angle theta in the first quarter, cosine would be positive. Sine also would be positive. If you have an angle in the second quarter, sine still is positive, cosine is negative. If you have an angle in the third quarter, sine would be negative, cosine would also be negative. If you have an angle in the fourth quarter, sine would be negative, cosine would be positive. So 104 degrees is somewhere around here. It's more than 90 degrees and it's less than 180. So 104 degrees is somewhere here. And here cosine is negative. That's why we got, well, if you look at the computations, we noticed cosine is -4 over 16.5. So cosine would be negative here. It shows this angle is greater than 90. It's the angle theta. So if theta is greater than 90 degrees and less than 180 degrees, it's in the second quarter. And when you are in the second quarter, cosine would be negative.
What do you mean by cosine is negative? Because the answer is still 100, like the angle is still 100. Oh, you mean that like the actual value of cosine, like cosine 100?
Yes.
Okay,
Yeah.
got it.
Yes, yeah. The actual value of cosine is -4 over 16. Is a negative number over a positive number. That number is going to be negative. Now theta is the angle which its cosine is negative, and then that angle is 104 degrees, right? The cosine of 104 degrees is negative. And yeah, we have another comment which is correct if you also want to know. Tangent here in the first quarter would be positive, in the second quarter would be negative, in the third quarter would be positive, in the fourth quarter would be negative. Okay, so we have these about these relations about the angles. Now, any more question here? Are we good? Are we happy with how we are computing the angle between vectors? Okay. Now the point is that the power of this method is that we can use the same method in three-dimensional space. So suppose in three-dimensional space we have two vectors, 1, 0, 3, and we have v2 minus 1, 1. And I'm asking you find the angle between u and v. Find the angle between u and v. And we should do the same thing, but it's a three-dimensional. Okay, again, spend a few minutes to solve this problem. I would wait. Here, in this case, which we are in three-dimensional space, if we have two vectors, u and v, inside three-dimensional space, you can still define the angle between u and v, right? When you have two vectors inside any vector space of any dimension, here we have two-dimensional space, you still look at the plane which contains these two vectors, right? There's a unique plane which contains these two vectors. And then you can look at the angle theta there. It's well defined. It really doesn't matter. Okay, we have 50, 58.9, we have 49. All of them are close to 50, almost. The answers are now closer to each other. That's good. I will wait one more minute. Okay, so where is u? The first component of u is 1, the second component is 0, the third component is 3. So u is the vector connecting the origin to this point. This is u. Where is v? V, the first component is 2, the second component is -1, the third component is 1. So we should go towards x direction by 2, we should go to left by 1, and then we should go up by 1. That vector which connects the origin to this point is the vector v. And then we want to see what is the angle between them. So we should use inner product using two different ways. U dot v is equal to, well, multiplication of the components, 1 times 2 plus 0 times -1 plus 3 times 1. We would get 2 plus 0 plus 3, which is equal to 5. That's one way to compute it, and we got the answer. The answer is 5. The second way to compute the inner product was by computing the length of u and v, multiplying that and multiplying by cosine of theta, the angle between them. So what is the length of u? The length of u is equal to the square root of sum of the square root of components. So it would be 1 squared plus 0 squared plus 3 squared. 9 plus 1, 10. It would be square root of 10. For v, it would be square root of 4 plus -1 squared plus 1 squared, which is the square root of 6. So this is equal to square root of 10 times 6 times cosine of theta, which is equal to 60 cosine, square root of 60 cosine of theta. On the other hand, we know these two numbers should be equal. There are two ways to compute the same thing. So this number, cosine of theta times the square root of 60, should be equal to 5. So cosine of theta should be equal to 5 over square root of 60. So cosine of theta is equal to 5 over square root of 60. Theta would be arc cosine of 5 over square root of 60. That's what we have. Now let's use our calculator to see what is 5 over the square root of 60. Its theta is 49.79, etc. So yeah, almost we got a lot of correct answers. I think all the answers were close. So that would be the cosine of theta. Okay. Okay, so we have that. That's the way to compute the angle between vectors, even in three-dimensional space. Now, suppose we have two vectors which the angle between them is 90. They are orthogonal, they are normal, okay? What would be their inner product? You can unmute yourself and someone can unmute and explain.
It would be 0 because cosine of 90 is 0.
Yes. And what about the other way? If we know, if we have two vectors which are non-zero, if their inner product is 0, it would imply they're normal to each other. And that's very important thing about inner product. Okay, so so let's write here, if theta, the angle between two vectors, it's 90 degrees, or pi over 2, then the dot product, or, oh, you can't see what I'm writing?
Yeah.
Okay, let me stop sharing and start sharing again. Continue. So if you have two vectors u and v, and the angle between them is 90 degrees, which is pi over 2, the dot product or inner product of them would be 0 because, well, we have length of u, length of v times cosine of pi over 2. But cosine of pi over 2 is 0. So the inner product of them would be 0. And that's important. So when we have two vectors u and v, say we have two vectors u and v, okay? The inner product would be, it would have its largest value if the angle between them is 0. Because inner product of u is the length of u times length of v times cosine of theta. What is the maximum value for cosine? There's a bound for cosine, yes. We know cosine is always between -1 and +1. That's the important thing about trigonometric functions. They're always between -1 and +1, right? So the maximum value for cosine is when it's 1. But when is it 1? It's 1 when theta is 0. When theta is 0, it means u and v, they have the same direction. So for example, this is u, this is v. The angle between them is 0. This is when the cosine is max, right? So u dot v in that case would be length of u times length of v times cosine of 0, which is 1. So if u and v are in the same direction, dot product would be, it would take its maximum value. When theta is pi over 2, they are normal to each other. It seems they are in completely different directions, right? They're normal to each other. They have completely different directions. Then the inner product would be 0 because cosine of pi over 2 is 0. When theta is pi, it means they have the even opposite direction, right? One of them is in one direction, the other one is in the exact opposite direction. U dot v would be the length of u times the length of v times cosine of pi. But what is cosine of pi? It's -1. So we should multiply this thing by -1. So, okay, let me summarize these. So when we have inner product of u and v, there are 3 important cases. One case is where theta is 0. then the inner product is equal to the norm of u, norm of v, cosine of 0, which is 1. This is the case where the inner product is maximized. And the vectors, they look like this. This is u, this is v. The other case is where theta is pi over 2. They're normal to each other. They're on different axes. In that case, inner product would be 0 because it's length of u times length of v times cosine of pi over 2, but cosine of pi over 2 is 0. And the last case is where theta is pi. We have u, the angle between u and v is pi. It means when the angle between them is pi, it means they are in completely opposite directions, right? This is u in one direction. The angle between them is pi, which is 180 degrees. And then we have v. In that case, inner product would be norm of u times norm of v times cosine of 180 degrees, or pi. But cosine of pi is minus 1. So we would get minus norm of u, length of u times length of v. Okay. And this is the case where the inner product is minimized. It's the least amount of inner product. It's minus length of u times length of v. Okay, that's the other extreme case. Okay, any question here?
I'm a little bit confused when you said if theta equals pi over 2, why did you say it's 0?
Oh, because, well, what is the inner product? Inner product is length of u times length of v times cosine of pi over 2, right? Mm-hmm. But what is cosine of pi over 2? Cosine of pi over 2 is 0. So we have length of u times length of v times cosine of pi over 2, which is 0. If you look at the table, you would see that. So it's length of u times length of v times 0, but anything times 0 would be 0.
Mm.
So inner product of two vectors, which are orthonormal, is always 0 independent of the length of u and v. So any two vectors you would take, u and v, which they are orthonormal, their inner product would be 0. Because cosine of pi over 2 is 0. And remember, in the second way to compute the inner product, we had this formula, length of u times length of v times cosine of the angle between them. Does that make sense?
Mm-hmm.
Okay, good. Okay. We can look at, well, it's not hard to see that directly too. So let's take two vectors which are orthonormal. Say v equal 2 and 0 would be here. And let's take u, which is 0 and 3. These are orthonormal, right? We can see that. What is their inner product? Well, we know it should be 0 because they are orthonormal, means they are, well, it's mathematical word to say two vectors. It means two vectors are, they have the angle theta between them. Yeah, theta is pi over 2. It means orthogonal. Well, maybe the word orthogonal is a better word. Yeah, let me use orthogonal, actually. I have not defined orthonormal. Thank you for reminding me. Yeah, but I have not mentioned that word. I didn't define that word yet. Say orthogonal, and let's say orthogonal, and it's the case where theta is pi over 2. So the angle between them is 90. That's what I mean, pi over 2 or 90 degrees. So, well, we know the inner product should be 0 because it's length of u times length of v times cosine of pi over 2. And length of u here is 2. Length of v is 3. Well, you can see length of v is 2, length of u is 3. Cosine of pi over 2 is 0. So we would get 6 times 0, which is 6. But we can also use the other way to see that. Well, the other definition of inner product is multiplication of components of these vectors. So I should multiply 2 by 0. Then I should multiply 0 by 3. Well, 2 times 0 is 0. 3 times 0 is 0. The sum is 0. So it doesn't matter which way we use, we can see the inner product of these two vectors is 0. When we have two orthogonal vectors, the inner product, the dot product would be 0. That's quite important. Okay, any more questions? No other question? Okay. Let's see. Okay, there's one more, there's another thing I want to talk about, and that's the so-called, okay, let's see. Is the lecture from yesterday posted already? Yes, I both the notes and the videos. The videos are on the YouTube, and the note is on the Blackboard. Yeah, 2 days ago. Thank you. Okay, so the next thing we should talk about, and it's quite interesting, is the projection. Projection, I would talk about this one, and then I would give you a short break. It's about projection of a vector onto another vector. What does this mean? So suppose we have two vectors. Suppose we have a vector v. Suppose we have another vector u. Okay. Now you can consider this new vector. Let's show it with u, say bar. Which, well, suppose there is a sun here in the sky. There is a sun here in the sky. It would look like something like this. Right? So the light would be, they are coming towards our vectors like this. We can look at the shadow of u on v. We would get the shadow of u on v, right? It's a new vector, actually, this shadow. This shadow is called the projection of u on v. So whenever we have a vector, v, when we have another vector u, we can find the normal segment from u to v would be a point. If we connect the initial point to that, that would be kind of the shadow of u on v. If there was a sun in the sky, that would be the shadow. We call this projection of u onto v. And that's quite interesting. That's very important. There is a question. You said inner product is max when theta is 0. But counterexample is if this thing is positive. Okay, the point is that the length of u times the length of v can't be negative. Length, okay, oh, the question is private. So you can write your questions usually like to everyone. It's good. I would encourage that because it might be the question of a lot of people. So someone has asked, you said inner product is max when theta is 0. But counterexample is if the length of u times the length of v is a negative number, then theta equals pi will have a bigger inner product. So the question is that what if the length of u times the length of v is negative? In that case, if you take theta equal to pi, inner product of u and v, which is length of u times length of v times cosine of pi, would be minus length of u times length of v. But since the length of u times length of v itself is negative, this is a negative number. If you multiply it with by another negative number, the whole thing would be positive. But that's not correct, simply because length of v and length of u are positive numbers. Length of a vector is always a positive or non-negative number. So their multiplication of two positive or non-negative numbers will be positive. It can't be less than 0. This is not possible. Okay, so okay, let's go back to the story of projections of vectors. So when we have a vector v, when we have a vector u, we can look at the normal segment from u towards v, orthogonal one, and then we can connect the initial point to that intersection. We would get a new vector. Let me connect them. We would get a new vector, which is kind of the shadow of u on v. We call that projection of u onto v. And now we want to compute that. How can I find that new vector? Let's show it with u bar. So u and v are given. And I want to find the coordinates of this shadow of this u bar. What is that? Let's look at an example. Let's say u is, say, 4 and 0. Let's say v is 2 and 2. What is the projection, or what is the shadow of u onto v? We want to compute that. Okay. So we have 4 and 0. 1, 2, 3, 4. So u is the vector connecting the origin to this point. And the other one, v, is 2 and sorry, I want to find a projection of v onto u. So the other one is 2 and 2, which is here. I want to find the shadow of u on v. This is the vector I'm looking for. This new vector, let's show it with u bar. I'm looking for this vector. The projection of u onto v. What I had written first was correct. Yeah, the projection, the mistake I made wasn't there. The mistake I made was here. Sorry, I changed everything once at least. So I have two vectors. I have a vector v and I have a vector u. V is 4 and 0. This is v here on the x-axis. And then I have a vector u, 2 and 2. And I want to find the projection of u onto v, the shadow of u onto v. And I want to see what that thing is. Okay, how can I find that? So, well, there are different ways. The way I'm going, well, let's write down the formula first and then discuss that more. This shadow actually is equal to inner product of u and v over length of v squared times v. Okay, that looks strange. If you haven't seen that before, it looks like a very strange formula. But let's use that formula first. Let's see if we can use it or not. So here in this case, u bar should be inner product of u and v. What is inner product of u and v? Well, we can multiply the components. 4 times 2 plus 0 times 2. Okay, that would be inner product of u and v. What is length of v? Length of v is the square root of 4 squared, which is 16, plus 0 squared, which is 0, which is 4. So the length of v squared is 4 squared times V times, oh, you can't see that part? Okay, let me go to the next page. If this thing is not visible for everyone, I would go to the next page. So V is 4 and 0, U is 2 and 2. The projection of, this is V, this is U, the projection of U onto V is this thing. We want to find this. I said the formula for this is the inner product of U and V over the norm of V squared times V. Okay, now the inner product of U and V would be 4 times 2 plus 0 times 2. Length of V is square root of 4 squared plus 0 squared, which is 4. So the length of V squared is 16. So here we have 16. And then, yeah, sure. And then we have the vector V. That is the formula for the shadow of U1. So let's compute that. 4 times 2 is 8. 0 times 2 is 0. The sum is 8. We have 8 over 16 times V. But what is V? The vector V is 4 and 0. 8 over 16, we can simplify it. It's 1 over 2. So it's 1 over 2 times 4 and 0. So it's 1 over 2 times 4, which is 4 over 2, and 1 over 2 times 0, which is 0 over 2. Okay, 4 over 2 is 2, 0 over 2 is 0. So this shadow vector should be 2 and 0, which makes sense. I mean, if V was 1, 2, 3, 4, if this was V, and if the vector U was 1, 2, and 1, 2, if this was vector U, if you look at the shadow of U on V, this is the vector you would get. And it is exactly 2 and 0. So yeah, this is the projection of U onto V. That's the way to compute these things. Okay, maybe just solve one more example of this thing, and then we can have a short break. So we can do the same thing in 3-dimensional space. We can have this projection inside 3D space. So let's say I have a vector V, and I have another vector U, right? And then I can assume there exists a sun here now. And I can look at the shadow of U on V. There should be angle 90. We should look at the normal segment coming from U to V. And this would be the shadow of U on V. We use the same formula. The formula is the same always. The U bar is U inner product of U and V over the norm of V squared times V. Okay. So let's say in our example in 3-dimensional space, U is 1, 2, 3, and V is say 2, 0, 4. And we want to find the projection of, U onto V. Okay. So,
I have a question.
Yeah.
Why do you keep on saying, like, in the other problem, it was also like projection of U onto V? If it was projection of V onto U, would it change something?
Yeah, of course.
Or
so
would it
it's
just,
like,
would it just switch the V and U values? So instead of it being for the denominator, instead of it being the length of V, and then V would just be the length of U.
yes. And
Okay.
also, yeah, so projection of U onto V, well, I mean, both geometrically and algebraically are different. So if this is V, and if this is U, first of all, the projection of U onto V, U onto V, would be this vector. It's the shadow on V, the shadow of U on V. If you were looking for the shadow of V on U, it would have been this vector. You should have kind of, you should suppose you're looking at the shadow of V on U. It would have been this vector. This is shadow of V on U, right? And also in the computation, projection of U onto V is U dot V over norm of V squared times V. Projection of V onto U is V dot U over norm of U squared times U. So the role of U and V would change in the equation. So you should be careful. This V, there's U and there's V. U is the thing we are looking at its shadow. We are looking at the shadow of U. And V is the thing we are looking at the shadow on V. So it's the projection onto V. So they have completely different roles. So if we have two vectors, 1, 2, 3, and what was the other one? 2, 0, 4. If this is U and this is V, if we are looking for projection of U onto V, it would be inner product of U and V over length of V squared times V, which is, well, what is the inner product of U and V? It would be 1 times 2 plus 2 times 0 plus 3 times 4. What is the length of V? The length of V is the square root of 2 squared plus 0 squared plus 4 squared, which is 20. So the length of V is 20. Length of V squared would be 20 itself. And then we should multiply this by V. Okay, what do we get? 2 times 1 is 2, 3 times 4 is 12. It would be 14 over 20 times 2, 0, 4. We can simplify this. 14 over 20 is the same as 7 over 10. So it would be 7 over 10 times 2, 7 over 10 times 0, which is 0, 7 over 10 times 4. We should multiply the components by this number. We would get 14 over 10, 0, 28 over 10. That would be the answer. Now, I want you to spend just 1 more minute or 2 minutes to compute the other thing. I want you now to find the projection. I want you to find the projection of V onto U. I want you to compute the other thing. Okay, so think about that for 2 minutes. I would write down the answer and then we would have 10 minutes or 15 minutes break. Okay, let me say that one more time because I forgot to record this last part. So if U is 1, 2, 3 and V is 2, 0, 4, in order to find the projection of V onto U, you should use this formula. U times V over norm of U squared times U. Inner product of U and V is 14. The length of U is the square root of 14, so the length of U squared is 14. And then we should multiply it by U, which is 1, 2, 3. 14 over 14 is 1. 1 times U is 1, 2, 3. So that's the projection of V onto U. Okay, here you go. We have that. We have the answer. And okay, a lot of people got it right. That's quite good. Okay, so let's have 10 minutes break, a little bit less than 10 minutes. Let's come back at 12, okay? Is that good? Okay, then. You know, one important part of doing math is to know how to solve problems. right? So I want to spend some time in our every meeting to kind of help you to get a handle of kind of solving math problems. I would start with kind of puzzles because they're easy to understand. You know, I want to help you to see how you can be maybe more creative towards solving some mathematical questions. So let's start with some, say, simple examples. Okay. Every question I tell you, I would give you a few minutes. You can think about it, and then you can just answer the question. You can unmute yourself and answer the question. Okay. Okay, so let's start. Suppose there are, so these are not directly related to multivariable calculus, and every time I might not spend more than 10 minutes. It's just both as a break and also it's a good motivation. Kind of, I would teach you how to think about these mathematical questions. So suppose there are 24 pounds of nails in a sack, okay? Nails are like this. The question is that, can you measure out 9 pounds of nails using only a balance with 2 pounds? A balance with 2 pounds, I mean something like this. So you would put something here. If it's heavier, it would go down. And if the things you have on both sides are equal, then it would be balanced, and it would, no size would be lower than the other one. So we have 24 pounds of nails. We would measure out 9 pounds. How can we use this to measure out 9 pounds? Think for 2 minutes and then unmute yourself and give me the answer. Are both pans 9 pounds or the total? No, not the pans. This is the tool we are using to get 9 pounds of nails. We want to, so we have 24 pounds of nails. I want to have 9 pounds of nails. I want to use this tool to measure 9 pounds of nails.
Should I say the answer or wait?
Oh no, let's answer in a minute, okay? So let's everyone think a little bit. So let us all think about these problems a little, and then after 2 minutes, you can unmute yourself and give me the answer. You want to unmute your, I think you wanted to give the answer, right?
I mean, sure.
Yeah.
So I guess you split it in half so that the 2 balances are even, and you take 1 half of it, put the other half to the side, and split it in half again. So it's 6 and 6. So both sides are even. Then you take 1 half, put the other half to the side, and split it in half again. So you have 3 and 3, and then you take the 6 that you put to the side, and you take 1/2 of the 3 and 3, and you have 9.
I see. Yeah, that is correct. So let me explain that one more time, and if it's still vague, you can ask me. So we have 24 pounds, right? We can put some amount of nails here, some amount of nails here. One might be heavier. So for example, this side might go down, right? If it's heavier, we can add a little bit of the left side to the right side, and we can do that until we find the point where these two pans are in balance, right? The situation where we completely divide the nails between these two pans. So we can completely divide them between these two. In that situation, we must have 12 pounds here and 12 pounds here. Is there a question? Did I hear something? The answer, Dylan's answer is also correct. Does anyone have a question? If there's a question, you can unmute yourself. Okay, so then we would have 12 pounds and 12 pounds, right? Okay, so let's move this 12 pounds here. So we would have 12 pounds here. We don't need that. Let's move one of these 12 pounds away. So here it would be empty now. There would be nothing here. And of course, the left-hand side would be heavier. This side would go down. Now we can start to move things from the left side to the right side. At some point, we would find a balance again, right? In that moment, we should have 6 pounds on each side because the whole thing was 12 pounds. We have balance now, so they should be equal. It should be 6 pounds. Let's move this 6 pounds here. Let's move this 6 pounds here. So we have 6 pounds. Let's move these 6 pounds of nails here. So here, the right-hand side again becomes empty. This would be empty. We have 6 pounds on the left side. It would go down. Okay. So let's start to move nails from the left side to the right side. Let's move them one by one. Let's move some nails here. At some point, again, we will find balance. They would be in balance because the whole thing is 6 pounds. Each of them should be 3 pounds. Okay, we have 3 pounds here. Bring this 3 pounds here. We had another 6 pounds here. Bring that 6 pounds here. Together, they would be 3 plus 6 pounds, which is 9 pounds. This is what we were looking for. Okay, we're going to have to chop a part of the nails to get exactly 9 pounds. Maybe better than nail. Okay, maybe rather than saying we have a bag of nails, maybe it would be better to say we have like an amount of water, you know, and we want to get another amount of water. Maybe that would have been a better example because yeah, it's not 24 nails, it's 24 pounds. Yeah. Yeah, okay. There are some discrete and continuous problems. I understand that. Doesn't really matter. Okay, so that would be the first question. If you're still confused about that, you can ask. Okay, let's move to second question. Okay, so suppose we have a wooden stick. Say it is 10 meters, okay? And suppose there are some ants on this wooden stick. Okay, so I would give coordinate to them. This is the point 0. Here it's 10 meter. Say here is here's 5. here is 4.5, here's 3, this point here is 7, this point here is 8. Okay, I just marked some points on this wooden stick. And these blue points are ants. So each of these blue points, if we put them under a magnifier, what we would see is something like this. That's not how an ant would look like, but something like that, okay? Not really, that's not how an ant look like. An ant would look like this. So if you put this blue point under and a magnifier, this is the ant we're going to see. Okay. Okay. So okay, the point is that they're walking in different directions. So this blue ant would go in that direction. This ant goes in this direction. This ant goes in that direction. This one that direction, and this one in this direction. Okay, so they are just going in different directions. Now, an interesting thing happens when two ants get to each other. So if, for example, if you look at the ants on the point 7 and 8, so we have an ant here, we have an ant here, when they're going towards each other, at some point, these two ants get closer and closer, and they, at some points, they have contact to each other. They get to the same point, and then it's when they have contact to each other, they go back. So if there are two ants, these are the ants, they're coming towards each other. When they get to the same point, they would go back. They would go backwards, you know. They're like two balls, like contacting each other, and then they would reflect and they would go back, okay? So for example, this ant, let's call it ant A, ant B, they would get to this point, and then ant A would go back, and then ant B would go back. And then when it goes back, it would have contact with the other ants. You know, there are a lot of ants, they would have contact with each other. Now, what would happen is that, for example, when this ant and this ant, they have contact, the ant which is at point 3, when it goes back, at some point, they would get to the end of the stick. And when they get to the end of the stick, they would fall down. They would fall down. The question is that how much it takes for all ants to fall down. How much does it take? How much does it take? Yeah, I would tell you, for all ants to fall down, if their speed is the unit. So their speed, the speed of ants is equal to 1 meter per second. How much does it take for all of them to fall down? Think about it for 2 minutes and then give me the answer. Yeah, yep. Yeah, if their speed is 1 meter per second, and if the wooden stick is 10 meters, how much does it take for all of them to fall down? What is the moment where the last one falls down? Okay, is the question clear? Okay, I take it as yes. Or maybe no, let me see. Okay, yeah. So suppose rather than kind of reflecting, coming A and B coming closer and closer together, being at the same point and then reflecting, Suppose the other case where A and B are coming closer and closer. At some point, A and B, they would be in the same place. And suppose in the next second, A and B would pass through each other rather than reflecting. So the difference is that in the first case, A was on the left side. It would get closer to B, they would have contact. A would go back towards the left side. In the second case, A is on the left side, gets closer to B, they would be on the same point, and then A would pass through B and it would go towards the right side. It would continue its path. Well, if we don't know these ants, if we don't know their names, if we don't know which one is A, which one is B, what we would see in these two cases is that these two cases are equal for us. If we don't know which one is A, if I erase all the names A and B, if I don't know which one is A, which one is B, if I don't know the names of these ants, do I see any difference between these two situations? No, they're identical. Two blue points get closer and closer. At some point, they would be in the same spot. And then it feels though they're continuing their path. They would pass through each other. Okay. So if there is a question, if it's not clear, you can send a message to me. If it's, they're quantum ants. No, they're just ants passing through. Oh yeah. In order to pass through each other, they need to be quantum ants. That is correct. Is it clear? Is there any question here? Okay. Now let's go back. Consider the same question. Consider the same question. We have these ants, they're walking around. I want to see how much does it take for all ants to fall. But now I know, rather than reflecting, they just pass through each other. When does the last ant fall? Well, this ant, independent, for example, say this ant, independent of all other ants, is going towards the right side. It passes through all the other ants. It doesn't even see the other ants. This ant would pass through them. How much does it take for this ant to fall? Where there are 7 meters, its speed is 1 meter per second, so it takes 7 seconds for this ant to fall. For this ant, which goes towards that direction, takes, well, it would pass through the other one. It would take 4.5 seconds. For this ant, which goes towards right, it takes 5 seconds. This one passes through all the other ones, takes 3 seconds. This ant here is what gives us the answer. It goes towards left. It passes through all the other ants. Takes 8 seconds to pass through all ants and falls. And it is the last one, so it takes 8 seconds. We can completely forget about that reflecting problem, which I completely agree. It feels like we need simulation for these problems. But as you can see, if we change our perspective slightly, we can give the answer. Any question? Is it clear? If there is a question, raise your hand. Okay, yeah. Sure. Can you unmute yourself? Okay, let's continue. So a third question. This is a question I want to, if you know the answer to this question, please don't answer. Don't spoil it for others. It's a very interesting question. If you don't know the answer to this question, think on whatever comes to your mind, give me his answer. Suppose we have 3 turtles. Okay, let's give them name. Let's say, what should I choose? Let's say, okay, let's say the names are Leonardo, Raphael, and Donatello. We have 3 turtles. The turtles, they look like this. Okay. We have 3 turtles. Suppose suppose Leonardo says, so say Leonardo says, so they're walking in a line. Suppose we have 3 turtles walking in a line, walking on a straight line. Leonardo says, I am in front of the other 2. Raphael says, there is 1 turtle in front of me and 1 behind me. Donatello says, Donatello says the same thing. There is 1 turtle in front of me and 1 turtle behind me. I don't know if you can see it here. If you don't see it here, let me write it some other place. Okay, let me write also here. So Leonardo says, I'm in front of the other 2. I am in front of the other 2. Raphael says, 1 in front of me, 1 behind me, and Donatello says the same thing. 1 in front of me, 1 behind me. Okay, these are the things that are. How is that possible? What is the configuration? What is the order? Okay, think about that for 2 minutes and then tell me what is the real order here. How can it be possible? How can it be possible that one says I'm in front of the other 2, one of them says there's 1 in front of me, 1 behind me, and the third person also says 1 in front of me, 1 behind me. How can we manage that? How is that possible? Okay, think for a few minutes. Okay, you can answer. If anyone has an answer, you can just unmute yourself and answer. And yes, they can see behind them. They can look backwards. Yeah, they can see everywhere. Now, there are only 3 turtles. Let's wait a little more and then if you can, so maybe not on a straight line. Let me say they're on a line rather than a straight line. They are on a line. Well, tell me how it's possible, and then I would, if you're asking horizontal, if you know of another line which they can be on, it would make sense. Then that would be okay. Well, one person says they're on a circle. The point is that on a circle, it really doesn't make sense to say which one is in front and which one is, you know, who is in front of who on the circle. Does it really make sense? I mean, who is in front of who here? I don't think it would be possible to say who is in front of who. So at least not in the thing I am. They keep teleporting back. Oh geez, no, they're not. That would be, I mean, no, they're not teleporting back. It's a race and statements are made at different times. At the same time, they say, at some points, at some explicit time, they say these are the positions they have. So not at different times. Quantum entanglement, no, it's not related to quantum entanglement. They're turtles walking, and two are walking next to each other. Well, if there are two of them are walking next to each other, none of them is behind the other one. I mean, then they would say one is next to me and then one is in front of me. And the turtles are not mixing their dimensions. Yeah, any other answer? The one at the end turns around, and so he first faces someone, and then he has his back to them. No. Triangular formation. No, not triangular. Well, if, as I mentioned, triangular would be they're at the same spot next to each other. No, that is not true. Actually, okay, I would tell you the answer. Cut L to L. Okay, so actually someone has given the correct answer. It's obvious, they're lying. The only way it's possible is that they're lying. I mean, how can you believe the turtles which are speaking? They're just lying. I said, how is that possible? And the answer is they are lying. I mean, how can you seriously believe a turtle which is talking? Yeah, someone gave the correct answer. So I noticed someone. Well, someone asked if they're telling the truth, and Xian Wang, that was correct. Yeah, you saw through the question. Yeah, they're just liars. Don't trust talking turtles. That's the lesson we learned from this. Oh, really? Okay. Okay, doesn't matter. So let's continue. Okay, let's go back. Okay, that's good for a little, that was good for just a little thinking and learning how to work with these kind of more creative problems.